So this is a wide audience conference in which I will try to explain some ideas that are used in control theory in its application, more specifically to aerospace problem. And in the second part of the talk, I will, in particular, speak about the use of Lagrange points that were discovered some time ago, but that are used since 10 years in order to design space missions, in order to design low-cost space missions. So let me first start with some words on control theory. So we had a first talk this morning on control, of course, but since my talk is destined to wide audience, I have to tell some words in order to explain with simple words what is control theory. So first of all, control theory is thematics of mathematics, which is destined to understand how to control, how to guide, how to command a system on which you can act by means of a so-called control or command. So we had examples this morning with a car, and indeed the car is the most simple example that we have in control theory, although it is full of mathematical difficulties. But it is very simple to understand that your car is a system on which you can act, I would say, by means of turning the wheel and acting on the pedals in order to accelerate or to break down, and say that the very simplest control problem that you have is how to steer your system, which is your car, from a given initial point to a final point, which is your final destination, say. So how to guide your system. So given that first example, you understand that at least conceptually, that is from the mathematical point of view, it is not very different to control a car or maybe to control a space shuttle or satellite or a robot. You spoke about a robot. For instance, with a robot, I don't know, you would like to act on a robotic arm, say, in order to make some remote surgery, for instance. So you need some precision. But you can encounter some control theory in many other disciplines, in many other scientific disciplines, such as, of course, electricity, electronics. In that case, control theory is rather known as automatic. For instance, I don't know, you have a telephone like that. You would like to send an SMS or an email, but of course, when the SMS travels, it arrives at your mobile in an incomplete way. And given this incomplete information, however, you would like to reconstruct the signal in the most efficient way, say. This is the so-called branch of control theory, which is called observability, because from a given partial information, you would like to estimate as efficiently as possible the information, reconstruct the whole state of the system. Well, another example of guidance that you can encounter in chemistry, for instance, is the following. It is the question that is investigated by the French Institute of Petrol, for instance. You have a given petroleum, and you would like to to distillate it, to make some distillation in order to separate components and get a petrol that you can put in your car, say, or in some plane. So you have some distillation to do. And how does it work, the distillation? It is a control process in which you act on the temperature of the process. Because you have an evolving system which is given by the kinetic equations of the chemistry, and on which you can act by choosing a nice curve of temperature in order to have at the end of the reaction such or such component. So it is also a control process. Of course, we encounter also some control, and more specifically some optimal control in biology, medicine. There are many works about that. For instance, how to optimize a cancer chemotherapy, for instance. There are many guys in our lab, Bruno, who are working about that kind of question. So you have the evolution of a tumor, which is given by some evolution equation, but you add some drugs, some cancer chemotherapy, and you would like to know what is the best possible strategy in order to kill as many as possible tumor cells at the end of the process, but maybe not expending too many drugs. And there are also many applications in economics. For instance, you would like to earn as much money as possible if you are a bank, for instance, given some estimates of the market. Okay, so this is just to give several examples in practice. And so the main issues in control theory that I will try to illustrate without entering into mathematics. The main issues in control theory are the following. There are mainly 4 questions, I would say. The first question of which is the question of controllability. Okay, you have a system, you have an initial configuration and a desired final configuration. So first question, is it possible to steer my system from this given initial point or configuration to the final configuration? For instance, I have a car. Does there exist a way of guidance to steer my car to this final point? This is the controllability problem. Now, this is for a mathematician, this is a problem of existence. Does there exist a control law able to steer me to the final destination? When this question has been solved, most of the time the second question is, okay, but how to do it, how to realize this controllability problem, moreover by optimizing something. Maybe minimizing some consumption or maximizing some output, something like that. This is the so-called optimal control, which is actually the modern version of the calculus of variation, mainly invented by Lagrange. So I will also speak about that in one moment. Then another question, very important in practice, is the question of stabilization, because, so that I will illustrate also during my talk, because of course in practice your system has many uncertainties. You are not sure of the model, there may be some noise or something. But once a trajectory has been designed, you have to stabilize it. I mean, you have to make it as much insensitive as possible to any perturbation. Okay, this is stabilization. And the question of observability, I just spoke about it just before, is the following question. You are only able to observe only one part of the whole state, and given that incomplete information, you would like, however, to be able to reconstruct the whole state, to estimate the whole state of your system. Okay? These are the main issues, I would say, in control theory. So let me now illustrate the first question, which is the question of controllability. So given a system, I will mainly illustrate in aerospace because for 2 reasons. First, I am specialized in aerospace, and second, it is a personal passion, actually. So okay. So the question of controllability, I repeat, is the following question. You have a system, which can be a satellite in the present example. You have an initial configuration, say an initial orbit, and you have a desired final orbit for your satellite. So first question, is it possible to steer the system to this final destination? So when you are in your car, for instance, a very basic question is the following. These are cars, okay? Your car, and you are coming with your car, and you see that you would like to park your car here. When you do not know anything about a car, you do not know a priori that there are constraints on the wheels. So for someone who is not on Earth, say, he would say, okay, but bring your car here and bring your car like that. Okay, it's the simplest way. So let's do like that. This is what we can call the perfect parallel parking, like does this lady. I'm sorry because the videos are not of high quality. They are stolen on internet, as you can imagine. Okay. So this is a way to make some parallel parking. Well, okay, but everybody knows that it is not so much realizable. And in practice, everybody knows that we have some wheel constraints. It means that only the wheels that are at the front of the car can move. And moreover, there is also a constraint on the angle, but okay, let us forget about that. But what is important is that the wheels that are at the back of the car cannot move, of course. And you know that in order to make your parallel parking, you have to implement a movement that is not so easy, and that we have to learn when we learn how to drive a car. Of course, it is not easy, it is not natural a priori. Here is an example that, okay. So you have to, when you reverse your car, you have first to turn the wheels to the right, then at some inflection point, you have to turn your wheels to the left. Well, okay, I won't teach how to make a parallel parking, everybody knows. Of course, everybody knows how to reverse a car, but when you add a trailer to the car, it is more challenging, maybe. So how to reverse a car when you have a trailer, for instance? It is more difficult. Probably also, we all know how to do it more or less. Well, personally, this is not me, but personally, I have my own technique. I have a trailer, not a caravan, a trailer, a simple trailer. I just tie it out of the car, okay? I reverse my trailer by hand, and then I reverse the car. It works very well, okay? So this is an example with one trailer, but of course when there are more trailers, so this becomes more mathematics. I could not find any video on internet in order to illustrate that fact, but here is a simulation of how to realize a parallel parking of a car with two trailers. It is not obvious. So it is from Scilab, simply. But the movement is not at all intuitive, I would say. Okay, I'm completely unable to do that. But mathematics can do it, no problem. We can simulate, we can, okay. It is easy to compute, actually. It is also easy to implement. For instance, it is used in practice when there are some big trucks, you know, with many trailers that are guiding some planes, for instance, in Toulouse. There are the pilot is a human, of course, but he's helped by computers. Okay, so this is an application. Let me give another application, which is maybe less obvious, also, although it is already not obvious. So Olivia Barbarou gave me some very fashion material. Okay. So let me take the problem of rolling an apple. So here is an apple, which is a convex body, say. And the problem is the following. Can you see with the camera? It's okay. You would like to roll the convex body on a plane or maybe on another convex body without slipping it. Okay. So, sorry. This is forbidden, but this is allowed. Okay. It can roll without slipping. And the problem of control that I investigate here is the following. I give a final point, I give an initial point with an initial configuration here, and I would like to steer the apple to some final point, which is here, for instance, but not only a point, also a configuration. Okay? I would like that at the end of the movement, the apple is exactly like that. Because if I do not give an orientation, of course, I am doing like that. And I'm coming to the final point, but not with the right orientation. Okay? The problem is to come to the final point with the good orientation. Okay? Okay, so of course it is obvious. How do we do it? We can roll the apple, and coming to the final point, I don't have the good orientation, so maybe I will do something like that to correct the orientation and come to the final point. Okay, okay. This is obvious with an apple. This is maybe less obvious with mathematics and maybe with more complicated systems. But it is an example also of a system on which maybe in order to act on it, you have to implement some kind of indirect movements, like when you reverse your car to make a parallel parking. So it is control theory. You have a non-holonomic system underneath. Let me show you a simulation which is done with MATLAB. Sorry. Where is it? Okay. So there is a software in MATLAB that was realized by Yacine Chitour and François Allouge. So let us consider an object which is a convex body like that. Let us realize some rolling. So let me give an initial position to the body, a final condition which is here with a certain orientation. Okay. So initial condition, final condition, and let us make some computation. So here there is a computation in real time. Here you can see actually the trace of the given path that you will follow, which is deformating, in order to fit to a final movement that works. Okay. So here is the trace on the object of the path. Okay, this software works actually with optimal control in order to be precise. So it gives me my transition in order to come to optimal control, because now that I have illustrated what is a problem of control, so imagine that now we have solved the problem of control. We know that we can steer a system, a given system that we have, from a given initial point to a given final point. But in general, when this control problem has a positive answer, there are an infinite number of ways in order to realize this control objective. Like when you are with your car, there are an infinite number of ways to make your parallel parking. But maybe among this infinity of ways, there is maybe you would like to select at least one trajectory which would be better with respect to the others in terms of a given cost criterion. For instance, you may want to realize your controllability problem by minimizing the time of transfer, maybe. Or maybe to minimize some consumption or maximize something, maximize some money in the case of economics, for instance. So, for instance, what would it give if we try to minimize the time while parallel parking? So it is maybe dangerous, but let us see that. Okay. I am not in the car, also. I do not know how to do it, but we can say it is a parallel parking in minimal time. Okay? I do not know how to do it. Maybe another way, also quite interesting. This one is an advertising at the TV, actually. And so maybe the last one for the pleasure. Okay, another possible trajectory in minimal time. Well, okay. But you can feel that probably realizing a parallel parking like that is a bit of dangerous. And probably it is more reasonable to minimize the consumption. And of course, when you minimize the consumption, you feel that the final trajectory that you will get is much smoother. This is just to say something very evident, but very important. The choice of the cost criterion will influence, of course, the form of the final trajectory. It is evident, but okay, better to say it in general. And well, I will not spend much time on that because all of you know very well, but we can say that historically, optimal control goes back to the famous brachistochrone problem, which is probably at the birth of the Lagrange calculus variation, which came next. And this very, very famous problem can be settled in few words. What is the optimal slide in the following mathematical sense? That you are given 2 points, say A and B, at some given altitudes, and you are searching what is the best possible curve, the plane curve, in the sense that if you drop a ball without any initial speed at the point A, you would like that the ball, or the child, comes down to the point B in minimal time. This is the brachistochrone problem. And as everybody knows, I will not make any quiz this time. The best trajectory is not the straight line, is not a circle arc, like Euler was thinking. He was wrong. Sorry? Galilei. Oh yeah, sorry, I'm mixing. But thank you very much. Galilei, not Euler. And the right answer is, as you know, the brachistochrone curve, which is a cycloid arc. A cycloid arc is just the curve which is let by a point, an apparent point, which is fixed on a wheel which is rolling along a straight line. Okay. Like on skateboards, it is used in skateboards. Okay. And so the modern version of calculus of variation is called optimal control. So it is more general, but the ideas are exactly the same, and go back to Lagrange. And just to illustrate some things that I work on, so I will mention several problems of optimal control that I am interested in aerospace. The first of which is a study that I made for the CNES several years ago, and which consists in investigating the optimal control of a space shuttle. So the space shuttle is turning back to Earth, or maybe on Mars. Okay, but the point is that at some point the space shuttle will enter into the atmosphere, and from that point, the objective is to put off the motors, so that actually the space shuttle can be considered more or less like a glider, without any motor, without any thrust. So a glider, probably it is better to say it is a big stone which is falling, but okay, it is a glider, so it is subject in particular to the atmospheric forces that are the drag and so the friction forces with the atmosphere. And so it means that when it enters into the atmosphere, the space shuttle is subject in particular to many constraints because of the friction with the atmosphere. In particular, the temperature inside the space shuttle should not overcome a certain maximal value. It is a very, very dangerous phase, actually. And the problem of optimal control that we can settle underneath is the problem of steering the space shuttle safely, if possible, to the final point, by minimizing what is called the total thermal flux of the engine, which is more or less a quantity of, well, the temperature should not overcome a certain maximal threshold. Okay, more or less. Okay. Also, recently I worked very much, and I'm still working with IADS Astrium, that is the leader of launchers worldwide, with the famous Ariane. And my task was precisely the following in the 4 or 5 last years. It was to design a new software that would be able to design automatically. That means without any human intervention. And instantaneously, so this is the challenge, of course, what is the optimal trajectory between 2 given orbits, an initial orbit and a final orbit, for the problem of minimizing the consumption. So what is new inside? course, the Ariane launchers work very well since years, since the end of the 60s or something like that. And since the end of the 60s, of course, people add a software in order to compute these optimal trajectories, but so the software is almost 50 years old, okay? So probably we can do better now. Actually, in order to compute a given optimal configuration, when they launched the software, they needed many hours of computation, sometimes several weeks of computation in order to compute just one launching configuration. Okay? This also explains that when there was some launching processes, if the meteo was not favorable, so they said, okay, it was stopped and it was postponed several weeks later. Why several weeks? Because it was needed to compute again the optimal trajectory. So, of course, at the beginning, when I discussed with people of Astrium, they required the instantaneous requirement, okay? Smiling. Okay, they did not believe in that, but we did it. We did it with mathematics of optimal control. It can be done. It can be done by working a bit, of course, and implementing some quite recent ideas of geometry and optimal control. And now this software is used by Astrium in order to launch the Ariane 5 launchers. It is used since last year, actually. It is integrated in their tools. Okay. Another challenge that I would like to mention before coming to Lagrange point, finally, is an important challenge which is related to the launchers, because this is the well-known problem of debris. As probably you know, the space beyond the Earth, beyond the atmosphere, is a garbage. It is full of debris everywhere. These debris are due to the older satellites that are not used anymore, and that are put more or less, when they are put, on cemetery orbits. So actually, it is a full garbage of debris. There are thousands of debris. Some of them, many of them are more than 10 centimeters, but some of them have the size of a bus. So it is very impressive, and more or less they are crossing the space very quickly, 7 or 8 kilometers per second. So it is very dangerous, of course. When there are some collisions, and there are many often with satellites, you can simply kill your satellite. So you can imagine that there are enormous financial stakes behind this kind of problem, because in particular, if you consider the geostationary orbit, it is full of debris. It is so much full of debris, actually, that if we do not implement any strategy in order to clean the space, probably in a few years, we will be completely unable to launch new satellites. So it means that the 3G, 4G, it will be stopped. We will have to come back to cables in order to communicate. So, of course, there is an enormous financial stake in order to design what we can call garbage collectors. So to imagine space missions able to collect as many as possible debris in the space. And for us, mathematicians, we are not working on the technique of collecting this debris. Okay, I do not know anything about that. But our task as controllers is to know how to design optimal trajectories. And it is a very complicated and very challenging problem, because it is both continuous and discrete. Because you have a catalog of debris, you have to imagine a path in this catalog, so a path between points, and then to realize also optimal trajectories between two debris. So it is mixing continuous and discrete aspects. So it is some kind of mixed optimization, we would say. And of course, we have some tools in order to investigate that kind of problem. But the problem is actually so much complex that nowadays no technique is able to treat efficiently that kind of problem. So it is a bad news. But bad news for the cleaning problem, but good news for us, the mathematician, because we have many problems to work with. Okay, so many ongoing studies on that kind of problem. Okay, let me come to the third question of control that I draw at the beginning, which is the question of stabilization. So what does it mean to stabilize a control system? Let me illustrate it with the inverted pendulum. So this is a pendulum. Okay, this is a pendulum. So attached to a fixed point, and here is a stable equilibrium point. Okay, but here is also another equilibrium point. I'm cheating a bit. Okay, but this equilibrium point is not stable in the sense that if there is a little perturbation of this unstable equilibrium, the pendulum will fall down, of course. So it is an equilibrium which is unstable. So now what is stabilization? Stabilization just means that I have an action of this system. So say here it is the movement of my hand, an horizontal movement of my hand. And with such an horizontal movement of my hand, and with my eyes, of course, I'm observing the pendulum, I would like to be able to stabilize the pendulum in a neighborhood of its unstable equilibrium, like that. Okay. So by the way, it is interesting to mention that you can make the experiment. I can give you this material. It is interesting to observe that. So actually, what does my eye look at exactly? Am I looking at the bottom of the pendulum or the top of the pendulum, intuitively? The top, of course, the top. Try to do it with some hat, so that you look at only the bottom of the pendulum and try to stabilize it. The pendulum will fall down, sure. This is a problem of observability also. I do not have time to enter into the details, but you can feel very intuitively that the pendulum is more efficiently observable if you look at the top of the pendulum. So intuitively, we look at more or less the top of the pendulum. I am estimating with my brain the full state, the whole state of the pendulum, and in function of that, my brain is designing a feedback, like you said, a feedback control, which is stabilizing locally this unstable equilibrium point. This is stabilization. Okay. By the way, stabilization is realized here by a robot which is the 2K Pi, which is in Fontainebleau, in the École des Mines. At the time when I was in Orsay, I was bringing my students of master to play with this robot. It was very nice. Okay. Let me come finally to the Lagrange points. So let me give an example of non-trivial stabilization that is used nowadays in space mechanics, and which is using the Lagrange points. So what are the Lagrange points? If you look at the dynamic equations of three bodies in the space, then it is well known that these equations in a moving frame have 5 equilibrium points. Historically, so of course I'm not sure of anything historically, you understand, but you can correct me. Historically, actually the three first equilibrium points were discovered by Euler, and the two other ones, the L4 and L5, were discovered by Lagrange, and so Lagrange won, and all of them are called nowadays the Lagrange points. So how to understand these Lagrange points? So you have a three-body dynamics in which you have two bodies which are very massive, such as, for instance, here, the Sun and the Earth. And the third body is a stone or satellite or something of mass almost equal to 0 with respect to the two others. So you can, of course, imagine that between the Sun and the Earth, there is a point, probably, so this point L1, where the attraction forces of the Sun which is to the left, and the attraction force to the Earth are exactly annihilating. Okay, so there is an equilibrium point. The point L2 is maybe less intuitive, but think that we are in a moving frame, and so you have to add the centrifugal forces. So here, at the point L2, you have to the left the attraction force of the Sun plus the Earth, and to the right, you have the centrifugal force. It is the same for the point L3, and for instance, for the point L5, you have the attraction of the Sun here, attraction of the Earth here, and the centrifugal force here. So there are exactly 5 equilibrium points in these dynamics. But actually, so it is also interesting to investigate what are their local stability properties. Actually, the third points are naturally unstable, which means that if you drop your stone or your satellite not exactly at the point L1, but just in a close neighborhood, it will not stay in a neighborhood of the point L1, and then it will go its way and rotate around the Earth and the Sun, like that. It's the same for the point L2 and L3. It's exactly the situation that you encounter, so with some degree of degeneracy, but we don't care, with the unstable pendulum. Exactly. It is a sort of unstable pendulum here. In contrast, the point L4 and L5 are naturally stable. So exactly like my stable point of the pendulum here. It is more or less the same phase portrait. So a priori, you could think that these stability properties of L4 and L5 are a very good news for space observation, because it means that if we put some satellite here at the point L5 or in some neighborhood in order to observe the cosmos, it is a very good place, because then you do not have anything to do in order to correct the movement of the satellite. Good news. Good news, but there is a price to pay, of course, because it suffices to look at the 3 body systems where the 2 massive bodies are the Sun and Jupiter. So when you look at the place where the points L4 and L5 are located, you can observe that there are many debris near the points L4 and L5. It is logical. There are some potential minima, and given the astronomical hazards, probably many stones have fallen inside these minima in the past and cannot go out. So the bad news is that it is unavoidable. The sites L4 and L5 are dirty. They are not clean. They are full of stones. So they cannot be used to put a satellite in the place. It is not possible. So, okay, it is like that. Let us come back finally to the instability feature of the point L1, for instance. So finally, what is paradoxal is that the instability of these points is a good news, finally, for cosmos observation, because these sites are naturally clean sites. There is no stone. Well, unless we are very unlucky, of course. There can be a stone which is coming, but we would be very unlucky. Okay. And indeed, they are used. They are used since years. Let me give some examples of use of these Lagrange points. For instance, the point L1, which is exactly between the Sun and the Earth, is used since 25 years or something like that, because near the point L1 is placed the satellite SOHO, whose mission is to observe the surface of the Sun. And indeed, it is a quite good place. Why? Because, okay, the point L1 is unstable, but it is exactly like with the pendulum. With only few efforts, so with a few controls, I will be able to stabilize the SOHO satellite. This is the idea. With only a little quantity of of oil or with solar panels in this case, we are able to stabilize this satellite. So there are many, many objects near Lagrange point, but this is just to give 3 examples of them. Near the point L2, which is at the opposite of the Sun with respect to the Earth, there will be last year the next Hubble telescope, which is called the James Webb Space Telescope. It is an ideal place in order to observe the cosmos because it is at the opposite of the Sun. Okay, and what is funny is that the point L3, which is at the opposite of the Sun, so it is behind the Sun, we can never see the point L3. But in the science fiction literature, actually at the TV in the 60s or 70s, something like that, there was a very bad series, so very bad, but it is funny, that was called the inhabitants of, the man from Planet X. And so the authors imagined at that time, so they knew the Lagrange points, this is what is funny, they imagined that at the point L3, there was a hidden planet that we cannot see because it is behind the Sun, it is invisible to us. And on this planet, of course, there were nasty inhabitants who were about to invade the Earth, actually. So, well, it is the man from Planet X. So very, very bad movie, but it is funny anyway, too. Okay. So let us do some non-trivial dynamical system theory. And with such a mathematical theory, we can prove that, so it is already known since 30 years, of course, that near the Lagrange points, which are equilibrium points, there are many, many, many periodic orbits. Many, and also many almost periodic orbits. For instance, near the Lagrange point L1, there is a family of orbits that topologically are exactly circles. These are the most famous ones, and they are called halo orbits. But actually, you can encounter all possible Lissajous orbits, so also orbits which are drawing an 8 or a triple 8, or and so on. So all these periodic orbits do exist. They are invisible, of course, but they do exist in the neighborhood of Lagrange points. And so, actually, they can be used, and they are used. They are used, for instance, for the satellite SOHO, which is not exactly put near the point L1 between the Sun and the Earth. Because if it was put at the point L1, it would be impossible to communicate with SOHO because of the perturbations due to the Sun. So actually, what the engineers imagined is to put the satellite SOHO on a large amplitude halo orbit around the point L1, so that we can communicate with SOHO. But it is put on a periodic orbit and then stabilized along this orbit. And also, there was a famous mission which has probably put some impetus on that kind of study several years ago. It was the probe Genesis, whose mission was to collect some space particles. So I do not know anything about that, but what I know is the strategy of guidance. So from the Earth, the probe Genesis was put on a halo orbit near the point L1, and then at some point, the mission was at the end, and it was decided to put just a little impulsion to the probe in order to put it actually almost on a heteroclinic orbit to the point L2. And with nice computations, they were able to make it come back to Earth almost without any energy, just an initial impulsion there and then nothing. So of course, because of that, you can imagine that the engineers got very, very much interested in these dynamics around Lagrange points, because they permit to imagine that we can design some far-reaching space missions that are almost for free. This is the interest. And so let me come to the last mathematical point, which is highly non-trivial, but that I will illustrate. You have to imagine that given such a periodic orbit around the Lagrange point, actually this periodic orbit generates what we can call some tubes. For the mathematicians, these are the invariant manifolds in dynamical system theory, unstable and stable invariant manifolds that I prefer, to name some gravity currents, similarly to the currents that you have in the ocean. If you take the Gulf Stream, for instance, so in the ocean you have the Gulf Stream. Okay, what does it mean? It means that if you put something at the west of Africa, you know, unless there are many uncertainties, and there are in the ocean. Okay, but forget about that. Forget about the uncertainties. If you put something at the west of Africa, you know that 6 months later, you will find it at such point, exactly. Okay? Because it will be driven for free by the Gulf Stream current. Okay, so it is the same in the space, actually. We have some kinds of what we can call gravity currents, which are due to the specificities of Lagrange points, and which also permit to imagine that you can put some stones, some satellites, along such a gravity current, and let it do. Just let it do. And let us compute where we can go. And it is possible, because in the space there are not many uncertainties, actually. Contrary to Earth. So what you have to imagine, it is not at all the result of some simulation. It is just a drawing like that. What you have to imagine is that the solar system is, in the solar system, you have many such sorts of tubes, which are gravity current, along which, if you put some stone somewhere, up, it will go for free and cross the tubes. Of course, the tubes are moving because everything is rotating, but all of that can be computed in a perfectly deterministic way. Okay, so this permits to imagine, to draw a sort of metro mapping of the solar system, but a metro which is completely for free. You do not have to pay the ticket. But the counterpart, okay, it is for free, but it is very slow. Okay. Imagine that you would like to go back home from the west of Africa just using the Gulf Stream. Okay, it will be long. It will be a long travel. It is the same in the space, of course, but with that kind of strategy, we can at least imagine some robot missions very, very far away with almost no energy. This is the interest. And maybe okay, I will. I'm jumping to my conclusion directly, and okay, I thank you.